Okay. So, good morning, guys. We are going to get started. Today, we are moving on to 3.2. 3.1, we talked about exponential equations. Exponential equations necessarily weren't a new concept. I believe you've been seeing exponential since integrated math 1. So, the inverse of an exponential is a logarithmic function. So we had two basic logarithms. We have the common logarithmic function. That is a logarithmic function with a base of 10. We can change the base on the logarithmic functions rather easily. I'll show you how to do that on other calculators like TI-84, TI-83. It's slightly, and when I say slightly, it's really not that hard, but it is slightly more difficult to change base than it is compared to Desmos. Desmos lets us write things out rather neatly mathematically as we would write them out on paper. So just as long as what you type basically matches what you write, we should be good. The other logarithm, we're not actually going to talk about this one too much today. We're going to save that more for next Monday, is the natural logarithm. So we talked about E being a number, and it is. So what we're going to do is, instead of doing it in one day, we are going to do this in 2. So today we're just going to focus on common logarithms. On Monday, we're going to focus on natural logs. It looks like, let's see. Okay, maybe it was just Desmos acting a little weird. So a natural logarithm is a logarithm with a base of E. We will just call that the ln. So here with this, a logarithmic function is the inverse of an exponential function. So if I say 4 to the third is equal to 64, my base of my exponent is 4. That becomes the base of my logarithm. The 64 goes inside of the log. So when I say log base 4 of 64, I'm asking myself 4 to what power gives me 64? Now this one we can actually kind of do in our head and be like, oh, well, 4 times 4 is 16. 4 times 16 gets me to 64. So it was 4 times 4 times 4. So the log base 4 of 64 is 3, because 4 to the power of 3 equals 64. So the logarithmic function with a base of a is defined as, we just write it, y equals the log of a of x. For x greater than 0, so we can't plug negative numbers into logs. Because when you think about a lot of stuff with exponents, if I square a negative number, it gives me a positive, right? So if I'm trying to ask, what power do I need to take something to get a negative? We start running into issues with negatives and exponents. So that's why it is only defined for positive x values, and our base of the logarithm is always going to be a positive number as well. That is not 1, because 1 to any power is just 1. So we're not looking at that. So if x is equal to a to the y, then log base A of x equals y. And we will again read that as log base A. So whenever you have that base, we like to say log base whatever our number is. So it makes it very obvious what the base of our logarithm is. An exponential function x is equal to a to the y can be rewritten as y, the power, is equal to log base a, so the base of my exponential of x, my answer. When evaluating logarithms, remember that a logarithm is an inverse. That means that log base a of x is, okay, sorry. I got slightly confused reading this. That means log base a of x is the exponent to which a is raised to get x. So again, log base 4 of 64 is telling me, oh, 4 cubed gives me 64. I know, that was a lot. Let's look at it in motion here. So for this first example, we are going to calculate this by hand because this is one of the few logs that's doable by hand. The next one we're going to use the calculator, but I'll show you how to do this one in the calculator as well. So log base 5 of 125. So this is my, okay, my smartboard is not writing where it's supposed to. Please excuse the gray screen for a moment. So I'm going to rewrite it. It says log base 5. So 5 is the base of my exponent. So the base of the log is the same as the base of the exponent. Now, I don't know what this is equal to, so that means my exponent is my unknown. That's my x. And that's going to have to be equal to 125, which is inside the logarithm. So what was inside the logarithm is what I have to get equal to. The base of the logarithm is the base of my exponent. So now we're asking ourselves, 5 to what power gives me 125? 5 squared, 5 times 5, that's 25. Not there yet. 5 times 25 is 125. So there we go. Got Obadiah in the chat saying, oh, it's 3. He's absolutely right. So yeah, our answer here is x equals 3 because, now you do not need to write this because part. I'm just writing this for more explanation because 5 cubed equals 125. Now the next one, it says use a calculator to evaluate. And when we think about this, if I'm starting to try and write this the same way, to be like 10 to the x is equal to 300, let's start looking at our powers. 10 times 10 would give me 100, right? Not big enough, so I'd do times another 10. But that'd be 1,000, right? So somewhere between 2 and 3, 300 should show up, right? that seems like a pain in the butt to try and figure out exactly where, right? Dealing with these decimal exponents, you're like, I don't know how to deal with that. That's where the calculator comes in. So we ran into a dead end here. So we're going to use the calculator. So I'm going to show you how to do this with Desmos. Let's get this projector mode. Come on. Just so it's a little bigger. Okay. So with Desmos, you can just type the word log. The default base for a log is 10. So you do not need to include that. And then in parentheses behind log, I just type 300. And there it is. And watch, if I do 10 to this power 2.7, or sorry, 4771 21. Notice this number keeps getting closer and closer to 300. The more decimals I add after this. So in all reality, I want 4 decimal places on any answer you're giving me, because we see even just 2 decimal places, a lot less accuracy when I take it to 3. That's pretty good. When I take it to 4, it's even better. You know, you could write out more than that, but 4 is my current recommendation. So if you're like, oh, I don't feel like typing it out, it's also on the keyboard. So if we go under functions and go under miscellaneous, the board is just the slightest bit off today. And go to miscellaneous, we see ln, that's going to be our natural log, log and log A. If you choose log A, we do that in a new line. If you choose log A, it lets you pick the base. So if I picked a base of 10 in here and did 300, we get the same answer. So remember, our default base is 10. That's the basis of our numerical system. So our default is 10. If you wanted to see, like the last problem, that was log base 5. If I did log of 125, we see that's way off. But if I change that base to say log base 5 of 125, I do see we get 3. So doing the change of base in other calculators is slightly more complicated. We will learn how to handle that, but Desmos makes our life pretty easy here. So I'm just going to show you that way, but I will show you change of base when it comes up in our notes. I think in section 3, or no, it might be section 4. Forget which one it was. I think it's section 3. So using the calculator to do this, we just got log of 300 is equal to 4771. Yep. So I hope that makes things feel a little easier. I know we said a lot of stuff there. Well, let's take a look at some basic rules of logs. Log base A of 1 is 0, because anything to the 0 power is 1. That's just the reverse of that idea. So our next rule, if I have log base A of A, that is also just 1. if I have inside of my log, if the base matches the base of an exponent in there, it just becomes x. It just becomes whatever that exponent is. We're going to talk about that a little more in depth when we talk about expanding and condensing. If I have an exponential that has a particular base a, and its exponent has a log of the same base, essentially they cancel out. So these would cancel out kind of like these are canceling out. Now, if I'm told the log base a of x is equal to the log base a of y, since they're the same base, you have to have the same number inside of them, right? Like if I said the log of 5 is equal to the log of x, well, they both have to be the log of 5, right? Do we have a question? Or? Unmuted accidentally. It happens. Okay. So for this, log base 7 of x equals 1. I'm actually just going to do a rewrite on this. So log of 7, my base is 7 of x. So that means it has to equal x equals 1. So my power is 1. What's 7 to the power of 1? 7. X equals 7. Another way to look at that would have been the following rule. Log base a of a is equal to 1. So if it's equal to 1, the base of my exponential, the base of my log and the number inside the log should match. I'm sorry, my board's going off again. And I know in just 2 slides I need to graph. So I do want accurate graphing. So again, sorry about the gray board. Okay. Next one, we're going to talk about the graph itself. So for any base greater than 1, the graph of a logarithm is always an increasing graph. So it might actually look weird with how it's increasing because basically it looks like it almost sort of levels off, but it actually does keep going up forever. So for this, since this is the inverse of an exponential, our domain and range gets switched around. For an exponential, our domain was all real numbers. That now becomes the range of a logarithm. Our range for an exponential was y is greater than 0. Well, when we inverse that, instead of being y is greater than 0 becomes x is greater than 0. And it turns out we now have an x-intercept of 1, 0, whereas an exponential had a default y-intercept of 0, 1. There is also a vertical asymptote at x equals 0, just like an exponential had a horizontal asymptote at y equals 0. So these graphs Okay, I didn't. My watch, I guess, is listening to me wanting to talk about asymptotes. It's reflected over the line y equals x. So let's take a look at that before they have us graph one together. So let's delete all this out. Come on. There we go. So here with this, if I say y equals 4 to the x, we get this exponential here. Now, since this has a base of 4, my log needs a base of 4. So I can say y equals, and again, I'm going to choose log base A. I can type a 4 in the little subscript area, and then x. And that gives me that red graph. Now, y equals x is the line I said it flips over. So when I do that, we would see that it does appear that this and this are inverses because they are reflected over the line y equals x. We can even see it with our x and y intersect. We do see those points are reflected. If you notice, it appears that the blue graph does have a horizontal asymptote at x equals 0, whereas the red graph has a vertical asymptote at x equals 0. So y equals 0, a nice horizontal asymptote here. X equals 0, a nice vertical asymptote over here on the other one. So last piece of notes, we're just going to sketch this graph. Now, does this move left, right, up, down, anything like that? So we think back to the transformations. It's nothing in front, right? So no stretch or compress or reflection. Is there anything like inside the function besides x? So that means no left or right movement. And there's nothing added or subtracted on the outside. So that means no up or down movement for this one. But if you think back to chapter 1, when we talked about transformations of functions, all those same rules still apply to this new function. So we saw it with moving like cubics and square roots and quadratics and all these different functions. This is just another function. All those shifts operate in the exact same way. So my critical information here, I know I have a vertical asymptote of x, or yes, x equals 0. So at x equals 0, I'm going to draw a dashed line like so. And I know I have a default x-intercept at 1, 0. So I want to plot that. Now that I have that information, I'm just going to do my best to draw this. If you want to grab more points, I know many of you have figured out how to make a table on Desmos. You could do a table, grab a few more points if you wish. I'm just doing a rough sketch. For my rough sketch, what I want to see is your asymptote and this point here. Even if this point gets moved left and up or right and up or whatever, even if that point's moved, just put that point so you kind of have your guiding point for your arc. So that it's going to go along the asymptote, curve up, and go like so. Now, again, I do want to stress, please make sure when you draw an asymptote that you do not cross it. You guys did an excellent job with that in 2.7 when we were graphing rational functions with their asymptotes. You did a great job with that knowledge. Oh no, these are my guidelines. I can't cross them. Saw so many great graphs with that. Again, if you are graphing this with Desmos, I do need to see where that vertical asymptote is moved to, if it does move. So please make sure you include that. Again, looking at the last set of quizzes, I saw many, many students doing that with Desmos in a great way. So, I said, hey, you need to include this on your graph, and you did. So great job there. So page 199, we are doing 16 through 36 even. So with a little bit of time, you could get a little bit of a start on it. Please make sure to try that today. This way, tomorrow you can come in with any questions you have, and I can address those. If you wish, the notes I posted, because this was all one file on 3.2, the notes I posted on Schoology have the second half of the notes where it gets into E, and it also lists what that homework's going to be as well. So if you run through this and actually feel good about it, you can start previewing what we'll look at next week. If you just want to wait for me to do that on Monday, that's absolutely fine. I'm just letting you know it is already posted, just not my recorded lesson. So let me stop our share and stop recording.